just a second. Few.
What happened? I think she left. I mean, by we were in mistake or something. She managed to rejoin. We will check with her. Oh, she's out again.
Admit, yeah.
Ah, yes. Yes.
So sorry, there were lots of, windows popping up, and I was just, I just closed them all together and I was out. So here I am in again, and I'm sharing my screen, and I'll go to my presentations. Can you see it?
Yes, ma'am. You can just put it
Fantastic.
in share mode.
Okay, and I'll make it bigger. Okay, I just want to hide this. How do I hide this? Stop share. Yeah, because, okay, fantastic. Yeah, I'm good to go. So, yeah, once again, thank you for having me here. And I'm really happy to be associated with this course of the Amity Center of Excellence in Astrobiology. And I congratulate all of you for having taken this effort to, build up this course. And it's not like a course doesn't build up in one day. It is a hard work of many minds, since time. So last 2016 till then, it got finalized now. So, and you are, whoever is here as students, you are the lucky batch of students, I must say, who are taking this course. And you'll be the pioneers. When you look down time, like 20 years after, you'll be the pioneers who are doing this astrobiology, astrogeology work in our country in a systematic way. Like all of us, we've studied some portion or the other, but coming to the planetary sciences and all, and making a link of our expertise to this subject was a hard way around. It was like this. But for you, it's a direct thing. It will be really helpful to you. And Introduction of Geosciences is very well organized course. I was looking through it, and I've been a part of it since the beginning. So thank you, Renata, thank you, Pavitra, and everybody who's amongst the staff here for this. So what I've done is, like, I'll be taking the entire course of geomorphology in this 1.5 hours that we'll be talking about. It's very simply done for because I was told that many of you are from the biology background and one from engineering background, but it will, because we all are seeing landscapes all around us, so it'll be very easy to connect with this course and the things that I will be telling you about. Many of these things would seem very familiar to you, because it's all that we're observing outside, we're putting it in a coursework now, and as studying it systematically. So I hope you enjoy this. And if you have any questions, do note it down. We can discuss on them at the end of the course, or even you can just raise hand, and we can take it in between also. So this is a very flexible class. So let's not be very formal. We'll talk in a very informal way, so that we can interact, and much things are we know what is geomorphology and landscape evolution by the end of this class. So I'll start with moving my slides. So the first thing is like, what is geomorphology? Yeah. So if I just say geo, you all know geo is earth, and morpho is a form, and logy is the study. So it is the study of the earth's form. So if I just it would be, if I put it in other words, it could be geomorphology is a systematic description and analysis of the landforms and the processes that create it or modify it. Okay, so here we are studying the landform. Now, what is a landform? That comes to our mind when we say systematic description or analysis of landform. So landform, if you see around, you have lots of landforms. Like if you are standing on a beach, you see this, nice beach. You see a cliff. You see ripple marks. These small landforms. Okay, so landform is an element of the landscape that can be observed in its entirety, its completeness or its fullness, and has a consistent form. So that is a landform. Okay. Now, when we talk about landform, then there are these great landscapes that have several landforms in it. So great landscapes, they are, they amaze you, they inspire you the most. They are beautiful structures of the planet Earth. So landscape are Earth's surfaces that are composed of an assemblage of subjectively defined lesser surfaces. Okay, so when I say that geomorphic system is a set of related landforms and processes, usually defined in terms of a dominant activity or a geomorphic agent like water, gravity, ice, wind, waves, etc. So when you look at this picture here, so you see, yeah, you see these cliffs, and you see these gorges, and you think how must they be formed. So if you just think, you say maybe it's a work of water and ice and physical weathering or dissolution. So all these things are the agents that have modified this landscape. Okay. So the history, when we come to the history benchmarks of geomorphology, I'll not go much in the history, but it's essential to talk about some. Even before Christ, like BC times, also the ancient world, they were talking about these the landscapes. They were talking about erosion and flooding. Some works of the Greeks and Pythagoras and Aristotle. So they do in their works, they do talk about erosion and flooding, etc., and cyclicity and an everlasting universe. So these were the terms in the BC, in the ancient world. Even when it comes to Christianity, there also we the Bible says of this catastrophic flood. So they knew that the floods happen, and the earth is very young. In the Bible it's there. But as time went by, there were several workers who came with an evidence of a long earth history, which is found in the rocks, which is found in the sediments, and they describe the landforms. So the revolution, it came when the natural sciences were in the 17th and the 18th century. So this the work of James Hutton on uniformatism is one, and the second was the Lyell's book on geology, principles of geology. Yeah. So these were the ones where they gave certain facts about the landforms and the landscapes. And as time went by, there were many other great researchers and scientists when they advocated the ice ages, the cyclicity of the formations, the processes, and the term geomorphology, it was coined in 1888 by McGee. So this was the first time when we were, hearing this term in 1888. So the majority of the work in geomorphology is followed after Andrew Gaudi, who emphasized on the aesthetics and the relevance of any landscape. Yeah, and he said that the landscape or the landform is the one which is attractive, which is and then he also was talking about its relevance to the society. Okay, so how would it be connected to global change, or what was its application? So there's a book by Gaudi of 2002 where he's written about the aesthetics and relevance of geomorphological research, geomorphological outreach. It was published in Geomorphology. Yeah, so it's a good read. You can see that it's very basic but very deep. So now geomorphology, it starts with the big questions that help us to identify the key issues. So whenever you see any landscape, so you see the hills, you wonder why the hills are here, why are they placed like this, why are the flat surfaces like this? Okay, so what would be the answer? The answer would be because the mountains are formed because of uplift. You all must have in some point or the other in school or college, you must have heard about the how the mountains are formed, the orogenic processes. And then when they are uplifted, then they are eroded by the agents like the glaciers, like the ice and all. And then the sediment is transported and it is deposited somewhere. So it gives a peculiar shape to these mountains. So you can see here crests are very horned, like horns and crests, typical of a glacial landscape, typical of a lacustrine landscape where finer sediment is coming through rivers and small streams and accumulating here, forming a lake or something. Similarly, for flat surfaces also, flat surfaces are they were not flat throughout the geological time scale. So they have been flat. They're mature landscapes which look flat today because of erosion and weathering and transportation and so on. For the aeolian deposits also, here you see a big, beautiful dune, yeah? So you know that in India, we have this Thar desert, we have hot, arid desert. So there we have this kind of an activity, and this is because of the aeolian deposit. Again, it's because of the transport and deposition by the wind action. So the process and the landscape feature, it goes together. We travel here and there, and we see that the mountains have different shapes. So either the beautiful shapes of the mountains, so they, again, we can say that they are like this because of the process that created them. Okay, the process that is creating them is endogenic. Endogenic means inside the earth it's coming from. Okay, like the plate tectonics and upheaval, it's the process. Then then when they are there in place, it is the process that is affecting them afterwards. After they are there on the surface, then the process of erosion, weathering comes into action, in which climate plays a very important role. And thirdly is they are of this shape because of the material they are made of, the rock type they are made of. If it's a hard battle, it's resistant, it will stay as it is. Or it's like a craton, it will stay like that. But if it's a shaly material or some kind of sedimentary rock, it would erode faster. So you can see this is probably a sandstone, and by the wind action, it's become an arch. So it depends on the process that created them, secondly on the process that affects them after it is created, and thirdly on the material that it is made of. So these are three very important things that help us to know about these big landscapes, or in this case the mountains. So now for the processes or the agents, if we say, we know that earth has gravity, and anything that is on top, it'll move, it'll try to acquire a base level. So the water, the ice, it will trickle down the slopes, whether the glaciers or not. It has to come down, and when it comes down with the friction versus gravity, it erodes the material that comes on its way and deposits it wherever it gets a flat ground, or wherever its energy, its capacity to take it further is less. So it will just drop it down there. So that is why the landscapes are modified. It's a very active process. It is not every day it's happening. Some are cyclic, but some are, it just goes to one way. Okay. So geomorphology is also very important because it helps us understanding applications and the enjoyments of landscape. Like we saw the mountains, it made us happy, beautiful shapes, nice, great landscapes. So geomorphology is important. Then we also it is important because in these with these landscapes, whether they are the mountains, whether they're the coastal or dунal or the wherever, or the caves and all, then we need to understand the ability to predict and mitigate hazards. They are always associated with hazards because we know that agents are working on it. The water, the ice agents are working, the wind, it's always there. So that makes the slopes very, very, fragile. So there would be landslides in the mountainous region, soil erosion would be there, flooding in these, like the Gangetic Plain, the place I am, talking to you with. So that is that there we have a lot of flooding and all. And then coastal erosions where you are placed. So there is coastal erosion going on. So when we need know these landscapes, and when we study geomorphology, it helps us to at least predict the hazards that are going on, and if we are predicting and we know how to mitigate them, so we can make that we can make use of it. It's the applied aspect of geomorphology. And secondly, and thirdly is the resources that are there. Like we know in the beaches, lots of heavy minerals are there because of the wind action. So you can see those darkish colors in the sands. Yeah. So maybe, and of course, when the mountains are there and they're getting eroded, so what is deep down there? Maybe it's an economically useful mineral that is lying there. So it helps us in our ability to exploit the resources, whether it's a water resource, whether minerals are there, geothermal energy, like for the mountainous areas in the Himalayas. I'll come to it separately. So we can harness the geothermal energy, we can harness the tidal energy, and also our building stones. It all comes from these landscapes. Okay, these rock formations. Then the study of landform and landscape, like what is the question, and why, how were they formed? So this what and why of any landscape leads us to the geomorphological questions or the answers. Yeah, and then one more important thing is the relationship between the landform scale and the time. Like if you see this background picture, it's a big mountain top with no trees whatsoever. So you say it's above the tree line. So this picture of Ladakh, but when you just look at it, you could say that, oh my God, it would be millions of years old. Okay, but when you could just see this boulder here and only this part, you could say it could just have rolled last year from the hill above. So it depends. The time and the age is very important also, how we classify our geomorphological landforms. And landforms can be explained in terms of structure. Three things are very important: the structure of the landform, the process of the landform, and the time. Time is also a very, very important procedure. I'll explain you all this. So before we come to time structure and process, I want to say that geomorphology, it's not like easy. It's just not like seeing landforms and all. So it is like geology. It is related to all other disciplines. Okay, so the tectonics, the fault and fold movements, like Himalaya has a lot of tectonics, the earthquakes and all, so that comes in tectonics. Petrology is the study of the rock types. Yeah, in thin sections we see the rock types. Then the geochemistry, the composition of the elemental composition of the rocks. Stratigraphy is maybe this term is maybe new to many of you. It's the superposition. Yeah, so what was older, what was younger, what was younger. So in geology we have this geological time scale. So pre-Cambrian rocks are the oldest rocks, then Cambrian, and then the Paleozoic, then the Mesozoic, Cenozoic. Okay, so we just go like this. So stratigraphy tells us in which time slice we are. And in places it's not simple that oldest rock will be beneath the younger rock. Sometimes because of the folding and faulting, everything is like this and much of it is eroded. So you'll really have to develop the stratigraphical record first, and then you can you go ahead. This is for the geologists. Yeah, they do it that way. And then the climate. So tectonics, petrology, geochemistry, stratigraphy, and climate, they determine the geomorphology of the Earth and its region by controlling the principal influences on the landscape. So we've understood this part. So when I go to the field and I see some evidences from my observations on the landscape, it in turn constrains to the tectonic, to the petrologic, to the geochemical, to the stratigraphic and climatic history of the Earth. So by seeing a landform in field, I can talk about the tectonics, I can talk about the constituent of the rock type, I can talk about the stratigraphy and the climatic history. So it's both way around. So now there are, even in geomorphology there are many divisions. I won't call it groups, but there are several divisions on the in the basis of what you are seeing, like historical geomorphology. So in historical geomorphology, the geomorphologists, they see about how the landscape evolution has taken place from time to time. Then structural geomorphologist will talk about the relief of the rocks and how the mountain building has taken place, what were the thrust, where were the falls, where has the slip movement happened, and so on. Then in the process geomorphology would talk about the process that formed that part of the landform. And climate geomorphologists would talk about the climate that is affecting the weathering and the chemical and the physical weathering processes in a particular landform. But these all don't go differently. All of it is converged to, get a good picture. So because we all like in toto things, so it's always good to have a picture in totality. So now the things that we need to consider in landscapes and landforms and the processes that are creating and modifying them, the things that are driving control of this processes. Like I say, okay, a glacier is affecting the landforms in the mountainous region. But now, how is that glacier controlled? Okay, so in the Indian context, I can say, okay, we get this westerly precipitation from the Caspian Sea, Central Asia in the winter months, November, December, Jan, Feb, March in the Himalayan region, which replenishes these glaciers. So the forcing factor is something else. Okay, so it's not only the agents or the processes, but then the teleconnections also that come into play. Okay, then how do we interpret these landforms and to make predictions for the hazard assessment and mineral resource mining and so on. And so putting geomorphology into use is another form, as like applied geomorphology. So there are geomorphologists who are in these big industries and all, which give them the idea about the resources and the policies that are to be made. Okay. So surface feature is very important. Whatever you are seeing outside, whether it's a mountain, a flatland, a dune, or a beach, a cliff, that is very important. The surface process is very important, whether it's the wind, it's the cyclone or the tsunami or the water, whatever. The process is very important, and the material is very important, whether it's just a sand layer in the Thar Desert, whether it's a hard rock of the Himalaya, whether it's the Deccan Plateau, basalt of the Deccan Plateau. So the material is also very important when we characterize geomorphology. Okay. So again, I am repeating things because, yeah, I wanted just to go in straight into your head. So study of landforms and landscapes. So I hope you've understood the difference between a landform. Landform is a smaller, landscape is a big scenario. Okay, the big screen that you see from your eyes, you can see the Himalaya like this, you can see the ocean, beautiful. But the landforms would be the smaller features in that big landscape. Okay. So there are different types of landforms. There are hills, there are valleys, there are floodplains, there can be sinkholes, there can be moraine like glacial, etc. There can be many, we can name thousands, yeah. Then there can be types of landscapes, like types and types. How would you put in, what would you put in types? In types, you'll put whether it's a glacial landscape, whether it's a fluvial landscape, whether it's an aeolian landscape, or whether it's a karst topography, dissolution and all, caves are being formed. So that will be the types. Then the other one would be, how would the landscape be evolved? Okay. So in this I don't know whether it's visible or not. So this is a very young stage which we all have studied in our geography books in class 8, 9 and 10. So a young phase of the river, a mature phase of a river with meandering river and oxbow lakes, and then the older phase of the river when it's left its meanders and it's just kind of straight. Okay, so this is how a very young landscape, it matures and it becomes old, and when it's old, maybe due to some upheaval, it becomes young again. So but that this entire stage has a time involved in it. It's not a time of like a few years. It could be 10,000 years to make this, another 10 to 20,000 years to make this, another million years to come to this, from this stage to this stage. So time is very, very important. So the study of surface processes which are responsible for landscapes and landforms. So there are several subdisciplines in geomorphology now. Okay, one is the process geomorphology. So people have, from the types also, they've done different historical and all that. And then depending on the process also, they have subdivided the discipline. And then there is a current process, that is when you go out in the beach in Bombay, you see there's a current process. The waves are coming and going, that is there. Then there is a past process. Okay, so that past process, it leads to a paleoform, which we call the relic landscapes or landforms. So relic is something that is ancient, that has survived decay or deterioration. So that it's a relic. Okay, so not only the current process do we have to take into account, we have to take in account of the past process also. That really hence a lot for the historical geomorphologist, or to help us see how the landform has evolved through time. Okay, so both are very, very important. So again, it's the same figure. So initial stages, how the landform is there with lakes and all, this early youth, late youth, you can just divide it into different sections, then full maturity, late maturity, and the old age. So again, I said the time involved would be millions of years. Yeah. And if the system is very dynamic, so it could be a few thousands of years also. So that depends on the material. If the material is very, very, it could be eroded in a very fast faster way, and then deposition was there. There were lots of agents along with water working with it. Wind erosion was there and all. So that would accelerate the process. Yeah, so the time would be less. But if it's a sturdy kind of material, it takes years to make to be formed like this, to be eroded and all. So it will take a lot of time. Now, you see this is a satellite picture, and you see, yes. So what past processes create this relic landscape? If I ask you this with that question, and I ask you the other question, that what modern processes are modifying it? So you see, this is a image from Ladakh. So this is Leh, the capital, not the capital, yeah, the main city. So this is the Ladakh range. This is the crest, okay, and the drainage is coming out from here. Then I think this is a river, I would call it. Yeah, valley. Another valley this side, and this is the Indus Valley. So Indus Valley flowing very in a broad channel here. It's flowing the valley to valley distance is very less, so it's really flowing in a narrow gorge here, and then so on and so forth. Now, what are the processes here? So if I say what were the processes that created the relic landforms, were they destructional processes or constructional processes? Okay, but this is a relative term. I can say this valley and this wide valley is this is constructive when I just see the valley, but when I see the hills, it would be destructional. So they go side by side. Yeah. So it can be a constructional landform, relic landform, or a destructional relic landform. Okay. So so this is a relic landform, and it is destructional, but the valley is constructional, and it is still being modified. It is still being modified because we have a little stream. This is all green is there, so all that soil and all is being formed, and all this anthropogenic things that are getting into it is also modifying the landform. Okay. So the this rock cycle, you must have read about, because in the introduction to geosciences, this is a very important part about the rocks. You all know that there are three types of rocks in the earth: the igneous, the metamorphic, and the sedimentary rocks. The igneous rocks, they are from the molten lava. They could be superficial rocks like the volcanic rocks. If they are come out through lava on the surface, they are volcanic rocks. But if they solidify deep inside only the earth, they don't have they don't get a vent to come out. So they are the plutonic rocks, batholiths. And then there are sedimentary rocks, like when there are mountains. So anything in the ocean that is going today as a sediment, in millions of years time, it will form a sedimentary rock. So anything that is forming by the action of water is and sediment is a sedimentary rock. And then, because we are living on the earth's crust, and the crust is like not very thick. Under the oceans it's about 10 to 12 kilometers. Under the mountains it's about 80 kilometers, especially Himalaya, 84 kilometers. So beneath that is molten, the mantle, yeah, and it's liquid. So because of that, because of high temperature and high pressures, so the already formed igneous and metamorphic sedimentary rocks, they will be metamorphosed. So they would be applied to high pressure, high temperature, and their originality will they form metamorphic rocks. So these are the three types of rocks. There are n number of categories. They're beautiful rocks. If you go to a geology museum, so you could appreciate there. So similarly, like a rock cycle, there is a geomorphology involved in a rock cycle. So so every part of the rock cycle that occurs at the Earth's surface has a geomorphic consequence. For example, there is magma. Okay, as I just said, it will solidify and it will form rock. And in the process, if a tectonic process happens, like that happened for the Himalayan orogeny, Himalayan mountain building. So folding, faulting, tectonic uplift, and land subsidence took place, and we have this whole 2,500 kilometers beautiful east-west stretching the Himalayan range. So structural landforms will be built, like mountains, fault scars, rift valley, etc. Okay, so geomorphology is there right in forming from magma to a rock to forming a structural landform. So, and then rocks are weathered. The debris comes out, and the sediment erosion, the load, and the sediment deposition. So all around along this process, there would be weathering landforms will be built because of decomposition and disintegration of rocks and minerals by physical and chemical processes. And what would be the weathering landforms be like? There'll be soils, there'll be karst caves, there'll be talus cones, debris cones, etc. They, then on by sediment erosion, by detachment and transport by wind, water, and ice, there'll be erosional landforms like the river, like the glacial valleys, like the gullies, etc. And then when the sediment is deposited, and by the deposition by wind and water and ice, the depositional landforms will be formed, which are sandbars, alluvial fans, deltas, floodplains, glacial tills, etc. So, depending at every portion of the rock cycle, we have these landforms, and they get their names like structural landforms, weathering landforms, erosional landforms, and depositional landforms. Now I'll give you an example of fluvial landscapes. Yeah, so this is a beautiful picture from Ladakh, and this is the river Janskar, and this is the river Indus. So you can see, what a beautiful, color difference they have. And now in fluvial landscapes, what happens that you should understand that the river, that water, if it's like in form of a stream or a river, it will try to get into its base level. And what is the base level? Base level is the sea. Okay, so when a mountain river, it goes to the sea because it's learning, searching for its base level. All the rivers that are originated, even in the center of the continents, they find their way either to a basin, whether it's a big lake and all, like in the Central Asia and all the big lakes, and the rivers trickle into them because the ocean is far. But whatever the majority of the rivers, they'll find their place to the oceans. So there is a profound concept that water flows downhill. It abrades and it erodes the landscape. And so by abrasion, the erosion process happens. And it also creates erosional landforms like drainage patterns, like the cut banks. And whatever material is eroded, it carries it out downstream, whether it is in a dissolved form, it's dissolved as a sediment load, or a suspended load, or a bed load. Yeah, so the load is transported, and then wherever the river loses its strength, the load becomes is deposited, creating depositional landforms, and depositional landforms would be deltas, point bars, etc. So the base level is the lowest level that a river can erode down to, and gravity sets the water into motion, and ultimately the water is trying to reach the sea level. So local impediments to the flow create local base levels. Like sometimes, what happens is the ocean is very far, but the river in that particular region, maybe tens of kilometers of area, it will try to do a base level, and then it'll like cut like this. So local base levels are also created when we are talking about, a regional setup. So this is again, this would be the starting condition. Okay, and the red one is the erosion, and the white ones are the deposition. So initially, material is eroded from here, deposited in these valleys on the first order streams. Then it will be carried to the second order streams. Then in the catchment area, it will be only erosion, and deposition will be only in the valleys. But if you see, this is the starting time. This is after 10 years, you'll see a picture like this. After 100 years, you'll see a picture like this. And then maybe after 1,000 years, there'll be only erosion going on, because with the slope, the river, it has, acquired strength to wash away everything that is being eroded. So there's no deposition. Even the things that it had deposited previously, it's just taken it to the downer reaches to attain a base level. Okay. Now comes another very important thing. Okay, before that, we'll just talk about what is elevation, and what is denudation. Take it from one point. If we see, there could be uplift, and it could be, eroded. So elevation, basically, if we say the Mount Everest is 8,488 or something meters, so how do we measure it? We measure the uplift also, and we measure the rate of the glaciers and all, as act as bulldozing machines, and they are just scraping the top layers off. So exhumation, we call it. So the elevation would be a sum total of the uplift and denudation. Okay, so this has to be kept in mind. And secondly is the principle of isostasy. So what is happening is there are two theories, Pratt's hypothesis and Airy's hypothesis. So surface, surface, why aren't we seeing the Earth's surface plane? Why is it like, sometimes it's like this, sometimes it's like this? What is happening? So there were different theories given. So the variation in the topography can be compensated through two end member mechanisms: difference in the thickness of layers or difference in the density of layers. So what did Pratt say? Pratt's hypothesis is that, it is, he says that the thickness of the layers that the Earth is made up of is different, because silver has these are the density that are giving here, and so the less density slabs will come up. That was his theory. And Airy said, no, the thickness has to, density would be the same. It's the length of the slabs that make the isostatic compensation through the difference in thickness of the layers. Yeah. So this is Airy's hypothesis. But if we see it in practical, if we go outside and see it in a bigger term, when we see the Earth as a whole. So as I told you, the Earth is made up of crust that is about 10 to 12, 5, 6, 7, 4 kilometers here. There's the water column, there's the crust, very thin crust, and continental crust is about thick 80 kilometers. Now when we see this, so nothing of these small blocks and all comes, because it's all there. It's basaltic crust. So here what we see, that Airy's hypothesis, because then basalt is 2.9, and then if you calculate it like this, you still see that the Himalayan crust is because of the Airy's hypothesis. So it's the thickness, not the thickness, but the length of the crust that makes the surface or the crustal variations. Okay. So now, we have lots of time. Okay, so I'll talk a few minutes about this geomorphic scale now. So let's see how does the features, they relate to the age in the context of geomorphology. Okay. So we know that the Earth is the ultimate landform. Yeah, nothing is as beautiful as our Mother Earth. So I've taken this from the book Baker, 1986. So here, what has happened is this is the order. So there are 10 orders, order 1, order 2 till order 10. The second column is approximate spatial scale. So it would be, tens of thousands of kilometers, and it goes to millions of, square kilometers. Then characteristic units with examples are given here and approximate time is given here. Okay, so we'll just say the first order landforms would be continents and ocean basins that are big and they are huge. See the scale, 10 to the power of -7 square kilometers. And the time to form them would be approximately million to billions of years. Okay, they are the first order landforms. Now, the second order landforms would be smaller, slightly smaller. They would be physiographic provinces, they would be shield areas, and they would be the depositional plain. Like for the Indo-Gangetic plain, I can say it's it's a second order landform. Okay, and the time is, of course, it is in millions of years. Okay. Then the third order landforms, which are again the scale, now the scale is going down, yeah, just see. There'll be medium scale tectonic units, which would be sedimentary basins, which would be mountain massives and domal uplifts like this. Fourth order would be smaller tectonic units like fault blocks, volcanoes, troughs, sedimentary subbasins, and individual mountain zones. Again, the fifth order would be erosional and depositional plains like deltas, and you have major river valleys and piedmonts, etc. Then then again, sixth order would be medium scale erosional or depositional units like floodplains, alluvial fans, moraines, smaller valleys, and canyons. Okay, then seventh would be a small scale erosional or depositional units or landforms like ridges, like terraces, smaller dunes. Eighth order, very small, they would be hill slope sections, streams, channels. And again, smaller, ninth would be pools, ripples, river bars, solution pits, etc. And they'll form in maybe hundreds of years. And then very small would be fluvial and aeolian ripples, glacial stations. Even the ripples that you see every day, if you are standing near the lake and you see a wave coming, you see a slight undulation. So they would be formed in seconds, and but they won't their preservation would not be possible. So there are 10 orders of lands. Terrestrial geomorphological features which are which we take into classification of these landforms. This is again the same time, but the geological time scale here is given. Okay, so this is million years. So first order landforms would be right from the Archean. They started forming Archean, the Precambrian. They started falling through the Proterozoic era. Okay, through from 4 billion years to 2 billion years, 1 billion years, they started forming. And then second order landforms, they started on this platform. The second order landform started building from the Paleozoic era to the Mesozoic era. Yeah, so they were the geomorphic provinces, shield and platforms. Then the third and the fourth are the sedimentary basins and orogenic belts. They started in the Paleogene, Eocene. This is all the Cenozoic. This is a tertiary era. Okay, Miocene. So even a Himalayan orogeny, Himalayas started to build somewhere here, and today we are here. So they started building here. Then the fifth and the sixth order is the Pliocene. Plio and Pleistocene are just 2.6 million years from now. Okay, and then Middle Pleistocene and all this is just 100,000 years that we see. And very present are the river forms, and the human works are the just after 10,000, 20,000 years before present. So this is a way to put how the landscapes and landforms are formed, and what is the time it is related to it as we consider the geological time scale. Okay. So scale of landform, it varies over 15 order of magnitudes. Continents are 10 to the power of 7 square kilometers to micro scale features like ripples and glacial striations, like 10 to the power of -8 square kilometers, in centimeters it's given. So the age of the landform, it varies from 7 to 8 orders of magnitude, from continents, billions of years, to the ripples and pools, like just 100 years or something. Large landforms are more durable, they're longer lasting. Small landforms, they are created and destroyed easily. The rate of geomorphic or geological change slow for larger areas, and it's fast for the smaller areas. Okay. So there's also William Morris Davis' introduction of the idea of the landform that can be, it can be explained by three things: structure, process, and time. So just a few slides on the structure, process, and time. Structure, because I've already explained like what it is. So we know the structure is very important. The rock mass or the unconsolidated mass on which the landform is very important. The process is very important. It can be a constructive process, things are coming in, or it could be a destructive process. So that is there. And then the time. How much time are we talking in that? So when we talk about a landform, it is a result of the structure, its process, and the time of, at one time. Okay. So, for example, this is a limestone bedrock like this, and the process would be dissolution because, water and calcium carbonate just mixes and it results in cavities which are called caves, and it takes about 10,000 years for this process. So the rock could be very old. Paleozoic, yeah. Paleozoic is like more than 80 million years ago. And the process would start in Cenozoic and, take so much of years to form it. So similarly, in this picture, again, and that I showed you in the beginning. So it was a limestone bedrock. The process here that is taking place is weathering. And this would be the time from thousands to 10,000 years would take place, would be needed to form a structure like this. Okay. So now you see this delta, the Brahmaputra, Mississippi, and a Nile delta. So you see the structure, we know it's a delta, sediments, all of them. The process is by deposition and also by erosion. So that is why they become fan shaped. And the time would be some 1,000 to 10,000 years. Okay. So by seeing a landform, you can determine the time, the depth, the process, and the vastness of that particular feature. Now I'll come to the global synthesis of erosion. Like now, what people have done, you could see they have calculated the erosion rates. Yeah, so you could see like the Brahma. This is India, the Ganges and the Brahmaputra delta. Look at this. So much of sediment is coming to the ocean. Look at this Wang Ho and all the rivers. Wherever the rivers are draining into the lakes or the sea, so you have a higher erosion rate. So an attempt for the parameterization of the global rates were done, and it was easy. You could the river catchment, the total sediment load of the river, the mean sediment yield, and then you can just calculate it, the velocity, and then you can calculate the how much the sediment is coming to the ocean. So here it is, and since we know the slope, we know the slope of the surface, we know the elevations, then we know the rainfall statistics. We have weather stations everywhere in the globe now, and so we can work out work our way up river drainages by computing average sediment yield, the correlation of the measured rivers, and then it is turned into a global map of sediment yield or erosion rate. So wherever the red one is, it's 1,000 tons per kilometer square per year. So you can see all in the Indo-Gangetic Basin, in China, and in Southeast Asia, and this part of America and South America, we have these high erosion rates. And in some portions, like the Saharan dunes and all, there is no erosion because the activity of the wind is, it's cyclic, it's just churning. And then there are moderate rates between the coast. All along the coast, world coast. See the continents, you'll have this 10 to 15. So these are the, you know how the sediment is proposed and is coming, and where is it depositing. So we have these global map of sediment yield or erosion rates. Okay. So till now we studied about the landforms and the processes. So we processes like that, the processes that were acting on the surface, like the glaciers, like the water, like the wind. Now, what happens? What is climate? Okay, climate is, we know that it is the temperature and the precipitation. They both make up the climate, and then this climate has a major role to play in the in these physiographic provinces of the globe. Somewhere it's a wet rainforest, somewhere it's the tundra, somewhere it's the hot desert, somewhere it's the cold desert, and this is just because of the climate. So climate has to play a very important role in geomorphology, and so does the tectonics. So we all know that the entire globe has different lithostratigraphic plates which are moving the mid-oceanic ridge, and this is Africa, this is South America, and so we have these ridges, and here are the major earthquakes in these regions, where these are the regions where the crust is being created or the crust is being depleted. So for young tectonic activity, elevation and relief are direct expressions of tectonic activity. For old stable terrains, elevations and relief become expressions of relative rates of erosion. And ancient tectonic features must be recognized by the relations of rocks around them. So current tectonic activity is also mentioned by the seismology and the geodesy. And everything that is in between this is geomorphology. So how is the landform taking shape? So climate, I would just want to stress here that climate and tectonics, they take a major role. So I'll just hurry up with the 10 fundamental concepts of geomorphology. This is kind of a revision for you before we get to the examples from Ladakh on this particular topic. So we know the same physical processes that are operational today operated through the geological past, although not necessarily with the same intensity. So this is the Hutton's theory. Present is the key to the past. Okay. Geological structure is dominant controlling factor in the evolution of landforms and is reflected in them. Okay. You know this, I need not explain. We observe relief on this Earth's surface because of differential rates of geomorphic processes that operate at differential rates. Okay, clear? For this, geomorphic processes leave their distinct imprints upon landforms, and each geomorphic process develops its own characteristic assemblages of landforms. Okay, that's the fourth. As different erosional agents act upon land surfaces, they produce an orderly sequence of landforms: youth, mature, old stage, and so on. We've talked about it. Sixth is the complexity of geomorphic evolution is more common than its simplicity. So these are complex. Like you just cannot say Himalaya mountain. Lots of things. Sometimes it's constructional landform depth, sometimes it's destructional landform. So many things are taking place at the same time in one landform. So it's not simple. It's more complex. Little of the Earth's topography is older than Tertiary, because Tertiary is the time period like about 60 million years ago, and most is not older than Pleistocene. Pleistocene is the age at 2.6 million years from now. So Pleistocene started, we still are in the Pleistocene, although in the Quaternary era. Quaternary period. So we say this because Himalaya, they started building in the Himalayan Rocky Mountains in the Tertiary only. Okay, and Pleistocene also, because in Pleistocene there was this glaciation. The entire Earth was cold, it was covered with ice. So, and ice is a very strong agent, powerful agent to shape the surface. Glaciers, they act like a bulldozing machine, they just scrape off everything. So that is why they say little of Earth's topography is older than the Tertiary, and most of it is no older than the Pleistocene. Eighth is proper interpretation of present landscape is impossible without full appreciation to many fold influences of geology and climatic changes during the Pleistocene. Yeah. Appreciation of world's climate is necessary to a proper understanding and varying importance of geomorphic processes. That is also there. Geomorphology, although concerns primarily with the present day landscapes, it attains maximum usefulness by historical extensions. Okay, so these were the 10 fundamental principles of geomorphology that we learned. Now I'll take you to a journey to Ladakh, and there we'll see some major geomorphic landforms like in these pictures you see. So here you can see, the U-shaped valleys are there. There is this permafrost action here. These are the moss mounds. You have nice proglacial lakes. You have these terraces, fluvial terraces, lots of lacustrine sediment. Lacustrine is the sediment that was deposited by a lake. Yeah, you don't see a lake here, so this is paleolacustrine. And especially, when the river is cutting the the fan of the slopes, then you have the lakes and so on. So these are the major geomorphic feature landforms that you see, and maybe next year we all will be in Ladakh together to see all these. So basically, these features have a time in them, they have a process and the structure also. Okay, so now what is happening is this is again a satellite image of Ladakh. So we see a mountain ridge, and we see how the valleys are there. So the valleys and how the things are being deposited down valley, like this. And so see, these are the parallel mountain ranges, and you can work out on the feature if you just zoom in more. Similarly, here again, what do you see? Again, I see a big mountain, a ridge, a parallel mountain ridge here, some more, and then a slope, and then some kind of a drainage network, all over here. And because I know my surface in the earth so well, this is a picture of NASA JPL, University of Arizona, of the Giante Chasm, in Mars. So I know just by seeing the picture, I could make out this was a ridge, these are parallel ridges, and this is a valley, and there is some kind of a drainage network. So this is the application of geomorphology in recognizing the satellite data or the LIS images that we have from Mars. So now we did have a lot of workshops on why Ladakh is a terrestrial analog for Mars. We know Mars, our red planet, as a very dry, cold, rocky ground with dust devils. It has a lot of loose rocks. It has permafrost and ground ice, rock glaciers, hot springs, gullies, valleys, valley networks, potential rivers, perennial rivers, and poles. So the scientists have already worked out on this, and the literature on Mars tells us that there is geomorphological fidelity. Any terrestrial analog should have a geomorphological fidelity if it has all these. Similarly, we know that our red planet is made up of basalt and quartz rocks, and shales are reported from here. And the exobiological fidelity is that it should permafrost, evidence of water, where extremophile organisms can be studied. Okay, so let's go and venture into Ladakh now. This is a geological map of Ladakh. So Ladakh has a beauty that you have all types of rock exposures in Ladakh. You have this big plutonic rock. This is the igneous rock, Ladakh batholith. You have volcanic rocks. This volcanic rocks of Khardungla and Dras. This orange thing here. This part, Pangongso part, is the metamorphic rocks are exposed. So you have and you have the Tethan Himalayan sedimentary rocks, a thick package of all these rocks. They are the conglomerates, shales, and the sandstones. Okay, so in one place here, you can see the entire geological rock, the categories of rocks here. One. Secondly, the Ladakh, because it is a high altitude cold desert, yeah, altitudes are above 3,000 meters over sea level. And then, so there is a lot of physical weathering due to this frost action. So Ladakh is a place where 6 months you have it's cold, it's covered with snow. So a lot of physical weathering is there. So a lot of debris is like on the slopes here. You have good because of the mountain orogeny. You have lovely folds and folds in the rocks. You can see them there. If it had not been a hammer, so we could have said this could be anything from Mars also here. Similarly, here this is Sarkar 2019 paper. So here, he shows such lovely box folds, informal folds are there in this. These are 50 meters and very high rise images that he worked on. Fold interference patterns, hinge and eroded recumbent folds, and brittle fracturing also he could make out from these this paper which he did from Mars. And he did also compare it with some portions in Ladakh. Okay, so he could see extensive scree on the slopes, heaps of eroded rocks and debris, ripples which are inferred to as dunes, and all this. Okay, so I've put it here because it's, if you know the geomorphology of the surface of your own planet, you understand the process and the time involved. You can interpret these images which are sent to you by our satellites. Okay, so and then in Ladakh, like I'm basically a paleoclimate worker, and I look at the terrestrial archives of lakes for my paleoclimatic studies. So when we were digging, we dig for sample collection in Ladakh. We hardly could dig, more than a meter because this permafrost has come. Apart from the cryosphere, like these the ice and the glaciers, we have a big reserve of fresh water inside the sediments in Ladakh. Okay, so but because of in the present scenario of global warming, everything is getting melted and all. So even this active layer of permafrost is like going down. So that is a real threat to it. But of course, we do have a lot of permafrost in this area. Then, as far as sand dunes are concerned, when we go to Hundar, which is a small village in the Nubra Valley. So here you can see a beautiful, dunes all around. These are some pictures from the NASA Spaceward Bound India program in 2016. So all where 31 countries were represented, and they're doing the work all across Ladakh. Initial results from the dunes, of course, the dunes will have a lot of quartz because they are, silica. So quartz and feldspars are there. So there is XRD. The total organic content from some people had studied here, our group only. There were these interdunal lakes here. They are not in the season; they are dry. So from there, you could see that there were some carbonates and inorganic carbonate, as well as some organic content also in these dunes. We have such deposits. It is called the moonland. People who went there initially, they thought it's not the earth. If you just ignore these electric lines here, you could say that it is a picture sent to you from Mars. Yeah, so this is Lamayuru moonland. So you have places like this. You have, because now it's very, as I said, it's above 3,000 meters above sea level, and then there is a lot of wind action there. There is no vegetation to hold on the soil. There's hardly any soil, so there is lot of these dust devils all around Ladakh. And in the afternoon, it gets very windy. The winds are very strong in the entire part, and they're picking up this finer particle from the valleys, and they are putting it in the slopes or depositing it elsewhere. The other property or the other characteristic is its ecological diversity. in one place you can get in one place, I mean in the entire Ladakh sector, you can get hot springs. This is the Panamic hot spring. You have Puga, you have Chumatang, and then you get glacial lakes all over the Ladakh range. There are glacial lakes, and you get these big lakes with salt deposit. This is not snow or ice. This is salt. This is Sokar. A picture from Sokar. So here it is the best place for an astrobiologist to study the psychophiles, the thermophiles, and the halophiles in one place. Yeah. So if we again come back to the same slide and say whether Ladakh has a geomorphological fidelity to be called as an analog of Mars, we would say, of course, it's 100% of chemical fidelity with its all type of rocks that are exposed, and exobiological also we can study the extremophiles organisms in Ladakh very well. That is why we chose it to be the analog of Mars. So that is it for today. Thank you for your patience hearing. So I will come back to you. Yeah. Parthiv, yeah, are you there?
Yes.
Yeah. So yeah, that's it. What I had to show to the students today. I hope it was interesting, and I hope they're not sleeping. Yeah.
Ma'am, there's actually first thank you for giving the talk. I think there is a question in the chat box by Pallavi.
Okay, I just see chat box. Where will it come? Just give me a little time, yeah.
Yeah, no problem.
Yeah, here it is. Okay. I'll read it. My question is, does the formation of lacustrine sedimentary deposits different from that of the sedimentary process that takes place in the rocks, since lacustrine deposits have yeah. So okay, Pallavi, yeah. Next question. You know what happens? Lacustrine sedimentation is what we see at the present. Okay. Now, suppose the scenario changes and you have this bundle of sediments, and uh, you give it some time, maybe 100,000 of years. So this will become a sandstone, okay, or a clay stone or a mud stone, in the process of lithifaction or the rock formation. So the process that are happening today will give the rocks for the future. Okay, so if you see a mudstone sequence in some Shivalik hills or somewhere, you could say that it could be a lacustrine deposit of the past. The process would be the same. Okay, is it okay?
Yes, ma'am.
Okay.
I just have a follow-up question. Is it because of the density and temperature that these rocks undergo throughout time, which makes them harden up as the rocks that we see today?
It is only the time factor that is the most important as far as lithifaction is concerned, and it is also the apt environment that they get for lithifaction. Because today you see the ocean, and you see lots of sediment going in the estuaries and all, but maybe a million years from now, that would be just lithified and it would be the crust of that time. So the hard rock that we are seeing today anywhere, whether it's cliffs and all, had been a soft rock, in the past. So it's kind of a very slow cyclic phenomena that is taking place.
Thank you, ma'am.
Okay. Okay, so we come to the next question by Nilesh. Thank you, Nilesh. Yeah, I'm glad you liked it. What can atmosphere of a planet tell us about the geological activities of a planet? Can we predict any geological activity on the of the exoplanet just based? Yeah, I think you can. Why not? Because atmosphere of this planet, like atmosphere of the Earth, is so important, because whatever the climate is there on the surface today, it has to do with the atmosphere, with these eddies and all. I'm not an atmospheric scientist, but that is there. I'll give you a small example, maybe that could be near to the question that you've asked. Like 75,000 years ago, you know, the in Java, there was a volcano eruption. Okay, Toba ash, they call it, and that ash was in the entire atmosphere for hundreds of years, maybe. We see it in the sedimentary profiles in India also, and sometimes when we don't have dating techniques and we see this white layer, and then we can say, yeah, this is Tovash, this sediment would be 75,000 years ago. Yeah, this is older than that. This is like, it's like an index for the entire globe. So anything of the atmosphere, whether it is the volcanic ash, or the cyclonic things, or the aeolian deposits, they do have a effect on the sedimentation or the geological activity of the earth that is taking place. As far as exoplanet and all is concerned, so that depends on the data that you're getting, like which kind of data that you are getting. So that would be a different question, which atmospheric scientists, like the people from the IITM and all, they would be really, they'll be good to answer that. But I can say that it does have an effect on the planetary, in the geological activities. The atmospheric, any undulation or anything in the atmosphere has an effect on the geological or rock formation activities. Yeah. Is it okay, Nilesh?
Yes, he's replied. Thank you, ma'am.
Okay. Okay. Any other
Yes,
questions?
there's a question from Mohana Sai. He says, how are geomorphological studies important in selecting the landing sites for robotic missions on other planetary bodies?
Very, very important question. A very good question. The rover that US sent to Mars was done after a lot of study of geomorphology. They sent it to a basaltic crater-like environment, so that if just imagine, just you can just close your eyes and imagine the Earth, and then a little tiny rover going somewhere in the Earth. It could be America, India, anywhere. So such kind of variety. But if you know your Earth well, and you can know that sending it to lunar crater would help give me a lot of idea about the rock type, about the erosion and weathering patterns, and the time. So I would send my rover to that, or the satellite to that portion. So these geomorphological studies are the basis of understanding any exoplanet. So they're very, very important. So an idea really makes you well aware of what the other planet looks like, or would have. So it is very important, and people are following it not from today. Like whenever the Apollo missions began, they started geomorphology, doing geomorphology and geology, which are the basis of these planetary sciences. Yeah.
Okay, ma'am.
Any more?
Thank you. Yes.
Sorry, ma'am. Hi, ma'am. Just wanted to follow up. Just wanted to follow up with the same question. Do you think Luna 25 officials paid mission?
Pavitra, can you repeat the question? I could not hear.
Yes, Mohandas, I can't hear you properly. Do you want to type in the chat box, or do you want to try again?
Okay, ma'am. Okay, ma'am. Typing.
And any questions you have, please feel free to write to me, and I will circulate some notes to Pavitra, and Pavitra, you can just distribute it And
Definitely,
I've
ma'am.
made it for my ACSIR coursework also. So the not more. And this presentation, you've already recorded it, but I can
Yes.
also send it to you, so share it with you so that the details, because you cannot talk everything in 1.5 hours.
Yes, of course.
So it'll be nice. And if after reading the notes, if you have some questions, students, you please feel free to write to me. Yeah? My email address, Pavitra has it, and it will be nice to interact with all of you.
Yes, definitely, ma'am. There's one last question if
Yeah.
you have the time.
Yeah, okay. Yeah, this is, thank you. Okay, yeah, thank you that you liked it. I wanted to know how accurate is the prediction when it comes to hazards and how they can be related. How can the severity be reduced? And the mass, it's the mass and distance from this. Okay. First question is about how accurate is the prediction? You know, it is accurate because and it depends on the workforce in that area also. General predictions, you can say don't go to the Himalayas, don't travel to the Himalayas in the rainy season because they'll have landslides. Very general. Okay. So don't travel in the post monsoon season because there are lots of like slips and all. Don't go to the areas which have permafrost and ice in the early summers because permafrost melting happens and it all slices. The slope slides down. So these are general kind of predictions, but because there are a lot many institutes and all working in the disaster management strategies and all, they have equipments now. Like for the faults, they have these GPS systems which are monitoring every movement of the earth, so that they can predict earthquakes and landslides. But at this point of time, we are still building up on it. Except the weather patterns, we are not like 10 years ago we didn't know the weather patterns also so well, but now they are very accurate. You know that it's 24 degrees in Lucknow, and I know that it's 27 in Mumbai, because it's so accurate. We are not so accurate like there, but maybe in the coming years, when people yeah, or expertise develops in these, we can be 100%, we can predict these hazards. And then one more thing is, we can train the people to be to be aware of these hazards, and to the resilience, how to act when a hazards come. Hazards will come because they're so natural, because geomorphology, everything is cyclic. It's going on since millions of years to today. So it will go on. So there is no stopping, because the exogenic and the endogenic forcings in the earth are playing a role. So we need to act on it. Like the Japanese, they say earthquake is there every 5 minutes, but they know how to adapt with it. The government has made policies. So if for India is a big country, so we are not just talking about Maharashtra or UP or one of the Himalayan states. So we need to have that kind of expertise. But surely in the future, it's possible that we can predict hazards to the neck of the point, and the government make policies for how to mitigate them also. Okay. So, yeah, Lazi, I think that answers your question, and I go to the next one for Mayuri. Ma'am, would the mass of the distance from star be related to the formation of the tectonic plate? I think this question is uh, distance from the star means we are so aptly placed from the sun. If we talk about the Big Bang theory, yeah, so we just came out from the sun, and we are so aptly placed. So we are a living planet. Okay, the earth, I'm talking about the earth. So that distance does play a role in the life on earth. Yeah. But to be it a tectonic thing, it depends on the rock type. Although we are a part of the same, our geological constituents of most basic geological constituents of all the planets is the same. There is quartz everywhere, there is basalt everywhere. So it depends on the constitution when the planet was made. So where were the weak lines and where was it? So this is more internal of the solid core and the liquid mantle. So that depends. These lithospheric plates is the internal endogenic forcing that has led to it, not the tectonic. The first blast could come when the Earth was formed, but not the tectonic things that are going, the sea floor spreading or the mountain building that is going on nowadays. Okay, so so I think you got an answer. So yeah, any more? So we are nearing time also, 2 minutes. I think it was good that there was time for interaction also. Yeah,
Yes, definitely, ma'am. Thank you again so much.
thank you.
If the students have any concerns or questions, they can always get in touch with me, or and I can share your email ID with them as well.
Sure. Yeah, that would be nice.
Okay.
Okay, thank you everybody. Thanks Pavitra once more. Bye
No problem.
Rajita. And thank you students. Yeah. So this don't think it's our last meeting. This is the first meeting. Okay. We'll meet again and again. Yeah. Okay.
Okay.
Bye.
All right.
Bye.
Thank you.
Thanks
Thank you, Dr.
all. Yeah.
Shweta.
Bye.
आप
Okay.
सेशन को एंड कर सकते हैं हाँ
हाँ. Bye.